Okay, now that we've done all the hard work of nailing down these character tables for linear optics, it's actually pretty darn straightforward to extend these same ideas to nonlinear optics. So when we now look at the full beta, it turns out because this is a parametric process, in other words, starting and stopping in the same state, it always transforms, it must transform as a totally symmetric group A with an eigenvalue of 1. And in that limit, we can write this is the set of eigenvectors, all that yield an eigenvalue of 1. These are basically, they either have one or two elements in them with either equalities or inversions. And so this is really a set of 7 eigenvectors, and these are the relationships that we first identified through the guess and check on the fourfold rotational symmetry. Now, how do we take advantage of the fact that we've got this mu and alpha to simplify which ones are non-zero? And it does help quite a bit, because if we look at a transition of E symmetry, the transition moment is given by this. And how do we exploit that? Well, the key thing, and one easy thing to do right away, is to recognize that there is no Z component in the transition moment. And so therefore, the first rightmost index on the right, corresponding to the transition moment, everything that has a Z in it cannot contribute to a resonant enhanced interaction with E symmetry. So this one goes away, this one goes away, and this one goes away, and we're down to a set of 4 non-zero eigenvectors. And if we have a symmetric Raman matrix, then let's see, these two are going to be equal, and these two are going to be equal, which gives us just 2 unique combinations. All right, now we didn't take into account the fact that there's complex terms in mu and alpha. We know that if it's going to transform as the totally symmetric group, it has to have an eigenvalue of 1. So it should turn out that when we take the Kronecker product of mu and alpha, we should end up with no non-zero complex terms. And yet, if we look at these, we have, if we just take the product of mu, how come we don't remove these complex terms? And it'll turn out that we necessarily do, but it might not be obvious as to why right now. One thing we have to do right away, though, is recognize that we're not comparing apples to apples here. We have alpha 0n, in other words, starting in the n excited state and going back down to the ground state. And here, what we calculated in terms of this was alpha 0n. So we need to change that, and we do that by taking the complex conjugate. Alpha n0 is the complex conjugate of alpha 0n. And so now we're taking the Kronecker product of these two, and you can see here we've got mu x, and we're going to multiply that by, in this case, alpha xz. So this is going to be beta xzx. Will be corresponding to 1 times 1. If I take this negative I, or this plus or minus I, and multiply it by minus or plus I, I'm going to get a beta yzy, which is going to have also a value of 1 as the product. And so these are the two, that's a y, the two that survive to make, let's see, this relationship. And so it's hidden in here, but it will just turn out that of everything that survives, the product will always be real valued and recovering an eigenvalue of 1. For a second harmonic generation, where we're resonant at the second harmonic frequency, we now have something where we have alpha mu is now the product. So the first index corresponds to the transition moment, and we can remove everything where the first index starts with a z. So that corresponds to these, and what we're left with is this set of 4. In the case of second harmonic generation, the alpha, because if we're doing second harmonic generation, it must be a symmetric matrix because of the degeneracy in the frequency. And so therefore, these two are equal, and these two are equal. And so we have 2 unique sets of vectors corresponding to the symmetry allowed elements in molecular hyperpolarizability for second harmonic generation.